Today we're going to prove the law of sines, or as it's commonly known, the sine law or the sine theorem. It states that in any triangle with side lengths A, B, and C, and angles alpha, beta, and gamma respectively, and circumradius, so the radius of the circumcircle r, we have that A equals 2 times r times the sine of alpha, written here, B equals 2 times r the sine of beta, and C equals 2 times r the sine of gamma. Now we're only going to prove the last equality, and the other two will follow by symmetry of argument, of course, because there's nothing special about the side C. There will be two cases. The first is here, when all the angles in the triangle are acute, and the second is when one of the angles of the triangle is obtuse. Now if this is the center of the circumcircle, then this length is r and this length is r, and this triangle is isosceles. Also, we know that this angle corresponds to this arc, and this angle here with respect to the center of the circle also corresponds to this arc and is twice as large as this angle. So if this is gamma, then this here is 2 times gamma. We also know that in this isosceles triangle, taking the angle bisector that makes this angle gamma and this angle gamma makes a 90-degree angle here and is a median in the triangle. So this equals C divided by 2. Here we have a right-angled triangle with hypotenuse r, and one of its angles is gamma, and therefore this side is r times sine of gamma. And so C divided by 2 is r times sine of gamma. Similarly, the length of this side here is also r times sine of gamma. And so the whole side is 2 times r sine gamma, which is exactly what we needed to prove. C equals 2 times r sine of gamma. The second case is when gamma is obtuse. Then how do we prove that C equals 2 times r sine of gamma? We know that this angle gamma corresponds to this arc of the circle. And this arc, with respect to the center of the circle, corresponds to this angle here. And so this must be twice as much as this angle gamma, so this is 2 times gamma. And now, since the full angle here is 360 degrees, this one has to be 360 minus 2 gamma. Now this triangle is isosceles because this is a radius and this is a radius, and this angle is 360 minus 2 gamma. Therefore, this angle equals gamma minus 90. Now let's take the common median, altitude, and angle bisector of this angle. We got that this angle equals 180 minus gamma, and we have a right angle here. This length is c over 2, and this length is c over 2. Now consider this right-angled triangle, in which the hypotenuse is r, and this angle is 180 minus gamma. Then this side must be r times sine of 180 minus gamma. Similarly, this segment also has length r times sine of 180 minus gamma. Therefore, the length of the whole side of the triangle is 2 times r sine of 180 minus gamma. Hence, we got that c equals 2 times r sine of 180 minus gamma, which is almost what we have to prove. What's left is to see that sine of gamma equals sine of 180 minus gamma for all angles gamma. Indeed, if this point corresponds to the angle gamma, then this point would correspond to the angle 180 minus gamma. And this point are symmetric with respect to the y-axis. Therefore, the sine of this angle gamma would be this length, and the sine of 180 minus gamma would be this length. The vertical projections of this point and this point onto the y-axis are the same. Therefore, sine of gamma equals sine of 180 minus gamma equals the length of this segment. This is the optional problem. We have a triangle and its circumcircle, and these are two of the altitudes in the triangle. They form this triangle here, and we take its circumcircle, so the circumcircle of this triangle. We need to prove that this circle and this circle have equal radii, and here's the solution. Let the radius of this circle be r, the radius of this circle be r1, so we're going to prove that r equals r1. Let this angle be beta, and let this side be b. Then we know that this quadrilateral is cyclic because this angle plus this angle is 90 plus 90, which is 180. Therefore, this angle plus this angle is 180, and so this is 180 minus beta, which means that this angle here is also 180 minus beta because this is a straight line and this is a straight line. Now, applying the law of sines for this triangle, we get that b equals 2 times r times sine of beta, which we write here. And applying the law of sines for this triangle here, we get that b equals 2 times r1 times the sine of 180 minus beta, which is written here. And so, because b equals b, then this side equals this side. When we cancel out the 2's, we get that r times sine beta equals r1 times sine of 180 minus beta. But we know that sine of beta equals sine of 180 minus beta for all angles, and therefore r equals r1, which means that the radii of this circle and this circle are equal.